Here we're going to introduce the idea of entropy. Now, you can read through this. This will make more sense later times, but we do have the idea of the standard state. So at these standard conditions, this is the way this acts. This is how much entropy it has, how much energy it gives off or takes in, the voltages when we get to galvanic cells, and so forth. So we can have two very different things. We can have the entropy for this reaction the way you did it at this temperature with these amounts and so forth. And we can have the standard rating, which go back to these standard states that are assumed for the standard rating. Also sometimes called naught for zero, H naught, S naught, G naught, E naught, I've heard. So in case you run into that in college, you know. So entropy is the dispersion of matter and energy. So it's the spread of things farther out throughout the universe, and that has an energy component attached to it. So it's joules per mole that is spread out, and also in the bottom of the fraction is Kelvin. So it's really more like this. What gets a little confusing, by the way, is that delta S, entropy, is often related in joules, whereas delta H is often told in kilojoules. And that can get confusing and can get to be a booger. You need to have them match when you use them in the same equation, of course, otherwise your units don't match and you get the wrong answers. So the absolute entropy describes the entropy of 1 mole of a substance. It's not a process, okay? The absolute entropy, but we're going to talk about delta S, that is a process. So yes, we're usually more concerned about the entropy change. So the change is greater than zero. It's a positive when the entropy increases. And that's what nature likes to do, is increase the spread of energy and atoms and particles throughout the universe. The universe is getting bigger. It has been determined it is not coming back. It is a one-time shot. This gets very deep in astrophysics and almost philosophical about what the universe is doing, what it is, where it's going, and so forth. So delta S is less than zero. It's a negative when entropy decreases and it becomes less disorderly. And once again, we can do the sum of the products minus the sum of the reactants and get the current delta S rating for the system we're talking about at this point. We can also do Hess's law, which is the flip and multiply version, if we know the intermediate steps. So here's a review of the kinds of things that could increase entropy. And I hope it makes some sense that the molecules in liquids are running around more than in solids, and in gas way more than liquids. So this is an increase in entropy along here. One of the ones that also comes up quite a lot is an increase in gas molecules. So probably anything that increases gas molecules is an increase in entropy. This is 2 to 3. On number 4, I don't recall that coming up on the test. I would tend to focus on that this is going from 2 gas molecules to 4, and that's definitely an increase in the entropy of the system. Here we have a solid creating a solid and a gas. That's an increase. A gas going to solid is definitely a reduction in the spread of these molecules and atoms through the universe. So that is a decrease. So delta S is a negative value. Here we have 3 gas molecules and 1 gas molecule and a liquid. So that's going to be a decrease in entropy. The water is a lot less spread out than its atoms used to be. So it's a decrease in entropy. Delta S is a negative value. Here we have 2 gas molecules and 3 gas molecules. So that's an increase. These atoms are more spread out than they used to be. They used to be contained in 2 molecules, and now they are in 3. So that's an increase in entropy. Delta S is a positive number. In example 2, we can concentrate just on the gases because there are no solids or liquids. We have 3 gas molecules on the left and 2 on the right. That's a reduction in the spread outedness of the atoms throughout the universe. So delta S is a negative value. In this case, again, we're going to emphasize that the delta S standard value is based on running the reaction 1 mole of times. So then we have to multiply these amounts by 2 and 1 and 2, because if you're going to run it 1 mole of times, you need 2 of these and 1 of those and 2 of those. And again, we're going to take the sum of the products, there's only one of them, multiply by 2, and subtract out the sum of the reactants. Take that one and multiply by 2, and remember the negative distributes in here, and also subtract 1 times that, and that gives us our overall standard value, our delta S naught, our delta S standard value. Here we have the idea of Gibbs free energy, and we're finally getting somewhere with determining whether a reaction will actually happen. So what does nature want to do? It wants to decrease the heat in a system, the enthalpy, and increase the entropy in a system. So if you could do both, the process would be thermodynamically favorable. And I actually wrote that in down here. They love this phrase. This is the phrase from the test. They do not say spontaneous. And by spontaneous, by the way, we do not mean that it just happens on its own. We mean that once you get it going, it continues until something stops it, not just because you stop pumping energy in. It runs out of reactants. It is interfered with. Okay, and the classic example would be paper on fire. Once you get it going, it continues on its own. It supplies its own activation energy to burn the rest of the paper. It is thermodynamically favorable for paper to burn. Nature likes to release the heat and likes to spread the paper all over creation, right? In the form of the ash and all the CO2 and water that's formed, right? It doesn't mean that paper just leaps into the process of being combusted, and that's not what we mean by spontaneous, which is why this is a better phrase, thermodynamically favorable. Once you get it going, it tends to continue. If something's non-spontaneous or non-favorable, more to the point, in the forward direction, that means it's favorable in the reverse direction. I think that makes a lot of sense. Some piece of that that's non-spontaneous may be outweighed by the fact that another piece of the overall reaction or process is spontaneous. Not every piece of it has to be spontaneous. It has to be spontaneous in the final analysis. And then the third one, I suppose, is true, but doesn't really come up. So here is a very famous formula. And we're getting here to the final evaluation of whether a process or reaction is thermodynamically favorable, whether nature wants this to happen, and whether it will continue on its own in general. So this is Gibbs free energy. And that's what we're talking about. That's the final analysis piece. So the change in Gibbs free energy in the process of this happening is equal to the change in enthalpy minus temperature in Kelvin, very much in Kelvin, times the change in entropy. And I understand that enthalpy and entropy are similar sounding words, and you're just going to have to live with it because that is the way this works. So it has units of kilojoules per mole. Remember, we said that this is often reported in joules per mole. It's usually easier to convert this to kilojoules because this will also usually be reported in kilojoules. And when you subtract, you have to have similar units. So as a standard idea, I would recommend converting this to kilojoules. Just move the decimal left 3 spots. So the standard formation would be the free energy given for 1 mole of the substance that it has just on its own, being formed, 1 mole of the stuff from the elemental states. And the free energy standard of reaction represents the energy change, the free energy change in the process as was being described in the problem. So nature wants to increase heat release and disorder. So since this is an evaluation in a sense of both at the same time, it does make some sense that nature wants this to be a negative value. It wants energy to be released out of the system. And notice we're going to stick a negative sign on the delta S. So when this is a positive, it actually contributes to this being a negative value. So before somebody thinks that I'm contradicting myself, this being a positive value actually subtracts even farther into the negative realm and helps create a negative value of delta G, which is thermodynamically favorable and is a process that nature tends to continue on. So again, if delta H is negative, that tends to make delta G negative. If delta S is positive, since they're subtracted out, that tends to make delta G negative, and then it is thermodynamically favorable or spontaneous overall. We get a negative value for delta G. If this is positive, that's working against the process being spontaneous, and this is a negative, that's also working against the process being spontaneous. And in this case, the process is non-spontaneous. It is not thermodynamically favorable, which means the reverse of the process is favorable, which is what we said back up there. So when these are negative and negative, we get something that takes a little evaluation. When delta H is negative, we get something that nature does like. It wants heat to flow out of the system, out of the process. But if you're decreasing entropy, then that's fighting against the process continuing. And since this is a negative value, but we're going to take the negative of that, we get a positive. We end up adding here. And so what we need to do is keep this term below the value, the absolute value of that term. For instance, if we had -5 and we want this to be spontaneous or favorable, we need this to be less than +5. So what we can do then is have the temperature be so low that we get a number that doesn't add high enough that it turns our negative into a positive. That's why it says at low temperatures. At some low temperature, conceivably, theoretically, this should be less positive than that is negative, and we get a negative value for delta G. Let's turn that around, and when they're both positive, that's unfavorable in enthalpy, but it is favorable in entropy. And then what we need is a Kelvin temperature such that this is more negative than that is positive. So in that case, we want temperature to be high, a high Kelvin value, so that in the end, we get a negative delta G value. So there are 3 ways to calculate delta G. I just told you about one of them. And then the other 2 are repeats, essentially. We can have the sum of the products minus the sum of the reactants if we know these values, the delta G formation, like we did for delta H and delta S. And we can also use Hess's law if we know the delta G values for the intermediate or elementary steps on the way to getting the full reaction. That's the flip and multiply version again. On 3A, we're given the delta H of reaction, the delta S of reaction, and the temperature, which I can convert to Kelvin. So then what we have is the setup for this. So here's delta H minus, convert that to Kelvin, times the value for delta S. Remember to subtract this value out, and also remember to turn this to kilojoules. I mean, you could turn this to joules, but then your delta G is in joules, and that's not considered good form in a sense. Plus you get 142,000, which is a bit of a unwieldy number. So I would just convert the delta S to kilojoules by moving the decimal to the left 3 points, and grab a calculator and see if that's what you get. In this case, we have the delta G of formation, see that? So if you run this a mole of times, you're going to need 2 of that, 1 of that, and 2 of that. And it's going to be sum of the products minus sum of the reactants. But the other little trick I would write down is that the O2 in regard to the delta G is considered to be a 0 because it's an elemental state. And I realize we didn't do that with delta S. Delta S does have a value for everything because everything has some bit of disorder and chaos, but delta G does not have a value for the elemental states like O2. So we're going to multiply the SO3 amount by 2, and we're going to put a 0 in for the O2, and then multiply this by 2 and subtract it out, and we get that. Here we're given the intermediate or elementary steps on the way to the full reaction. And we're given the delta G standard values for those steps. Now, you could go and evaluate every chemical on every line. It's a waste of time. Once you've proven through logic what to do with one line, each line, you can move on. What I would do is find something that's unique. I don't see SO2 anywhere else in here. So SO2, I need to be on the left and have a 2 in front of it. Well, it's on the right with a 2 on it. So that's a flip. I need to flip this end to end, and that puts a minus value on that amount because I'm going to turn this around. So therefore, this value changes sign. Here I have SO3 and it's on the wrong side and I need it doubled. So this is a flip and it's multiplied by 2. So this is times -2. Then comes the more difficult part, and you could do this 3 different ways by evaluating these. I just grabbed this one. I need this to cancel out. It is not in the final equation. So this must cancel out. And I know that these two H2S's are on the right side and I need them to cancel out. They aren't anywhere else right. So this one needs to cancel out with this one. This is now on the right. This should stay on the left and I should multiply it by 2 so that I have 2 H2S's on the left and then 2 H2S's on the right. That will cancel out. And if you really wanted to go and evaluate these, you can, but as long as your logic is sound, it's pointless and you know what to do with these values, and then you can add them up.